So thanks for the introduction. Thanks for having me here and giving me the opportunity to present my topic in an extended talk in more detail. And I'm glad to take this opportunity to give you an insight into the world of microfluidics and the actuation of small droplets. So what can we do with electrohydrodynamic actuation of liquids? This effect can be used to manipulate the wetting state of liquids on solid surfaces by the application of electrical fields. So we can use it to manipulate the wetting angle of a liquid by the application of electrodes in our liquid and underneath to change its wetting state. So to change it from de-wetting, hydrophobic, to a wetting, hydrophilic state. And we can also use it to move droplets across a planar surface. So these methods by electrohydrodynamic control, they join some very relevant benefits, which make them very appealing for the use in microbiological systems. First of all, you can really manipulate very small liquid volumes up to nano or even picoliters. And the effects are completely reversible. So we are not changing any of our liquid properties here. We can change the wetting properties and back to the initial state. We don't need any movable parts that could wear out over time or that have to be designed in a very complex way into our system. And in the end, it can be driven at low voltages. So this is very good for mobile application, for handheld systems, and so on. So overall, we have a very good and appealing method to use it for droplet transport, fluid transport, microsystems for biological applications. So we can use this in two different ways. So first, we can pump continuous fluid volumes through a microchannel. Here is an example of an electrowetting driven micropump, which was created by another member in my group. And here you can use just electric fields and a structured microchannel to move a continuous liquid volume through a channel. I am working with droplet-based microfluidics, so I'm manipulating single droplets over planar surfaces, and these can be used to transport cells, biological samples, to sort them, mix them, and so on. This is appealing for lab-on-a-chip applications where you want to prepare your samples for further analysis. So to give you an introduction or an idea how these systems work, I show you the short overview of the basic working principles that we have for these applications. So when we are talking about microfluidics and electrical control, I think the most commonly known effect is electrowetting on dielectrics. And that means we can control the wetting state of a conductive liquid on a solid surface by the application of a field. So because the physical effect behind this is based on free charge transport within the liquid, it has to be conductive. So we are contacting the liquid directly. This is shown here by a wire which is pushed into our droplet. Another electrode is underneath our droplet. In between, there is a dielectric layer. This is to prevent current flow and unwanted effects, just electrolysis and so on, we don't want to see in our system. And on top, there is mostly always a de-wetting layer introduced, so Teflon or PTFE, to increase our initial contact angle to make the surface hydrophobic if we are talking about water. So now, upon application of a voltage, the free charges within the liquid accumulate near the surface, and at this contact line, this leads to a Maxwell stress, or a mechanical stress that distorts our liquid volume, and then we spread our droplets. Another working mechanism when we're talking about electrohydrodynamic control is based on liquid dielectrophoresis. So this is analog to electrophoresis as we know it from solid bodies. And this is based on polarization forces on dipoles in our liquid. So this can be applied to dielectric and conductive liquids depending on our frequency. So at high AC frequencies, the charge carriers and the liquid cannot follow the fast changing field anymore. And then we can also actuate these liquids like a dielectric. So now, if we are introducing inhomogeneous field to our dielectric liquid, the dipoles that might be permanently in the liquid or induced by the electrical field, they see a force which drags our liquid towards the electrical higher field intensity. So this is a volume force, so we move bulk liquid masses in contrast to electrowetting, where we just have this surface tension change. There was a very specific configuration of dielectrophoretic forces, which is called dielectrowetting. And here, by the application of interdigitated electrodes, so underneath our droplets, we can concentrate the dielectrophoretic force near our substrate surface. And by this, you can achieve an contact angle change as known from dielectric, although we are using dielectrophoretic forces. And this is the effect that I chose to work with on my substrate, as we can use it to manipulate dielectric and conductive liquids. So depending on the medium that we want to use to transport our biological samples, or it's not dependent on if it's dielectric or if it's a conductive liquid, we can use it for all liquids, basically. So now we're talking about contact angle changes. How can this effect be used to move a droplet from one position in our substrate to another? This is quite easy done by the introduction of an asymmetrical electrical field. So in the last slide, I showed the field distribution homogeneously above our droplet. But now, if we place sequential electrodes underneath our droplet, if we now introduce an electrical field, the droplet changes its shape asymmetrically. And this leads to a pressure difference inside our droplet. And this gives rise to initiate a bulk liquid motion, so we can move our droplet to another position. And this can be done basically without limits, so we can transport our droplets, our huge arrays of electrodes to mix and change different media with each other. So now, to make the design of such an dielectrophoretic driven system, looking at common applications that we can find, which are presented, they are mainly based on two different ways for the design. So one, here we can see an example, is based on interdigitated electrodes. So this is, has the advantage, it's a planar design, but it requires a relatively large number of electrodes. As we can see here, each electrode to drive the droplet to the next position is divided into two sub-electrodes. That means in the end, we end up with a relatively large number of electrodes that have to be contacted. Another approach is the use of a parallel plate electrode configuration. This has the benefits that we have a very good penetration of our electrical field into the droplet, but as it is encapsulated, we have no access to our droplet for any operations, and it requires the fabrication and design of two separate fluidic substrates. So for the design that I built, I decided to go for a very simple planar configuration, as we can see it here. This is designed to move 4 individual droplets between 2 positions respectively, and each droplet transition is realized by 4 electrodes. And in contrast to existing systems, these are just planar electrodes with a wave-shaped interface. This is chosen to increase the electrical field inhomogeneity in this region between them to improve the droplet transition. And everything is placed on a planar substrate. That means we can just use another chip as a lid on our fluidic substrate, and we can use sensor applications or anything that we want, and we don't have to change our sensor chip in order to operate it with our fluidic system. So the dimensions here for the droplet is about 900 micrometers. That corresponds to roughly 50 nanoliters. So it's really a microfluidic system here. Everything is based on transparent materials. so that enables an easy visibility with a camera through all operations. So it's a glass carrier chip, and the electrodes to actuate the droplets are made from indium tin oxide. This is a transparent semiconductor, and fluid walls are made from a dry film resist. I will come back to this in the next slide when I show the fabrication. Very important for actuation is the coverage of the entire cell with a polymer coating that serves as insulating and dewetting layer. So dewetting layer to increase contact angle and facilitate the droplet motion. So the fabricated design assembled to a silicon chip. This one is holding optical waveguide structures, but there could be anything you want on this chip. Is shown here with an assembled configuration. So the fabrication is done by very simple standard microtechnology facilities. So we are starting with glass wafers, which already have their ITO layer carrying. This is patterned by wet chemical etching. Then gold electrodes are deposited, so just to have a more easy connection to any peripheral electrics. Here, openings are brought in by sandblasting. Filling openings of very small dimensions onto glass substrates is quite hard because we cannot go for any standard etching techniques because this is too slow with thick glass. And micro sandblasting has shown very good results for this purpose to achieve openings with a diameter of down to 100 micrometers to dispense our droplet into the cell. For the fluid walls, a permanent tri-film resist is used. This can be laminated on top of our wafer. This has the benefit that it can be applied to pre-structured substrates, as we have it here with the filling openings. And the tri-film lamination also has big advantages for thicker fluid walls. Here it's 100 micrometers, because we don't need spin coating or anything else with a lot of excess resist and so on. And this can be just patterned by photolithography, and then the dewetting and insulating layers are brought on by chemical vapor deposition. It's not working. Now it responds. So let's go on. Here we can see microscopic image of the finally fabricated substrate. So here we can see our transparent ITO electrodes, the sandblasted openings, and here is an SEMB tile of the tri-film resist. And this might be interesting for anyone who wants to do fast fluidic prototyping in an academic institute or so on. This lamination was done with a standard office lamination device, which was adapted for this purpose. So you don't need any dedicated equipment for this. You can do it really with very simple equipment. The liquid system, here this is very specific as it is designed for the application in an optical system. These liquids are trimmed to have a very high difference in refractive indices. But basically, we can use any liquid combination with a high difference in permittivity as we are actuating by dielectrophoretic forces. Here, the ambient liquid is brought in by vacuum filling, and the actual droplet is dispensed by a pipette, which is connected to a high-precision syringe pump. And then we can push our liquid with a volume of 7 to 17 nanoliters right into our fluidic chamber. So why are we using a two-phase fluid system and not single phase? This is very beneficial for actuation by electrical forces, because if we have just one liquid, here for example, the droplet at the length like coal on a PTFE or Teflon coated substrate in air, we can see contact angle is about 90 degrees. If we introduce an ambient liquid here, the contact angle rises to about 160 degrees. And this high initial contact angle is very beneficial for actuation. We have less hysteresis and less sticking forces of our droplet to the surface, so we can actuate at way lower voltages. And also we can circumvent issues of evaporation, which is also very crucial for microfluidic systems. So now here we can see the finally fabricated substrate in a testing configuration. So this is simply mounted to a PCB by conductive glue. So also very easy to achieve with simple methods that everyone has in the lab. And the actuation here is done with a rectangular signal with a root mean square voltage of roughly 16 volts. Comparable systems with dielectrophoretic forces often use 100 volts or even more. So we only need very low voltages here. And this is not even optimized. So we can still optimize the thicknesses of the dielectric layers, and this can get even lower. And now for the actuation, why AC signal? Because of the pulsing, we first initiate like a slightly vibration of our droplet contour, and this helps to overcome sticking forces, and it also prevents charging of dielectric layers. So then we can just simply actuate the adjacent electrodes sequentially, and here we can see actual captures from high-speed video imaging. The activated electrode is here highlighted in red, and we can see when we activate the droplet at these electrodes, the droplet changes its shape and is dragged towards the active electrodes, and then can move from one position in the cell to another, and of course also vice versa. Looking at the motion profile of such a droplet transition, this was also captured by high-speed video imaging and analyzed by digital imaging processing. For this purpose, one edge of the droplet contour is just dragged over an entire motion circulation. And as we can see, when one electrode, here it is labeled as C, you can see when this one is actuated, we have a steep increase of our droplet position and also of the velocity, and the end position is reached asymptotically. That means if we have a look at the velocity, this goes towards zero. So this is also consistent with any theoretical calculations that we can make when we have a look at the dielectrophoretic force. So we can see you can really move the droplet like this, and we note that it goes towards zero, or it gets slower when it reaches the end position, which might be considered when making designs for such fluidic systems. Having a closer look at the contact line of our droplet transition, as I mentioned at the beginning, when we're actuating the electrode, we are changing the wetting state on one side of our droplet, and this can also be very nicely observed qualitatively. So here we have the contact line of our droplet magnified at 0 voltage. So it consists of 3 separate lines, and these can be seen from schematically the cross section like this. So we have dewetting behavior on top and bottom substrate, and then we can see the middle line, which is the meniscus of our liquids. And upon actuation, this line moves downwards, so we only have 2 lines indicating clearly a wetting behavior. So we have dielectroweting forces here, dielectrophoretic forces to decrease the contact angle and move our droplet within the fluidic cell. Another thing which might be quite interesting is the influence of the droplet that we are using. So depending on the viscosity of our liquids, the interfacial tension between our liquids, the droplets show a different behavior. So if we have a look at this droplet motion, we only looked at the so-called active edge. That means if we actuate this electrode, this edge is actively dragged towards this direction, and this passively dragged. So looking at a liquid which has a higher viscosity, this is about 80 centipoise, we can clearly see a deformation of our liquid shape, of our entire droplet shape. And if we have a look at the motion times of the active edge here with the circular points, it is way faster than the passive edge, which is about 2 to 5 times slower. Also something that has to be considered with the design of such microfluidic systems. In contrast, if we have a look at a liquid with a way lower viscosity, here it's about 10 centipoise, we can see active and passive edge move almost at the same velocity, at the same speed. We have not such a delay as we can see it from the higher viscous fluid. And also we don't see such a large change in the droplet shape. So this gives me to the summary and conclusion. So here I designed a microfluidic system that enables droplet transport by dielectrophoretic forces. And this is for the first time done with simple electrode structures. And this gives us the opportunity to design simple microfluidic systems to address both conductive and dielectric liquids based on the application that we are going for. And these can be used fully flexible with any system, as we can incorporate all our fluidic components on one simple design. The actuation voltage is quite low, and as I've mentioned, this can be decreased even more just by more optimization of the dielectric layers and also the shape and the voltage that we are applying, and the frequency, which is something I'll focus my research later on. And to continue with this, I want to move on with more open fluidic systems, so not with such like very strict fluidic dimensions, but just to have an open system to demonstrate droplet transport, droplet mixing and merging, and other basic fluidic operations on this platform. So I want to thank you for your attention. I want to thank everyone who supported me with this work. And here we can have a small insight into our clean room where we do the position and etching of our thin film layers.